Now it's time to move on and discuss relaxed consistency models. As we've seen, sequential consistency is far too slow to be implemented in a large parallel system. If you have a system of, let's say, more than 20 processors, you can't be in a position where any write to shared memory anywhere in the system needs to complete completely, in other words, be seen everywhere before the next operation to shared memory can go ahead. If you're in a situation like that, your program will run far too slowly. But the problem is, if we don't have that sequential consistency guarantee, then we can't be sure our programs will work correctly. We at least need some memory operations to be seen in order throughout the system. So one way around this is to have a safety net between operations, like something like a fence instruction, where if we really need operations to occur in order throughout the system, we just put a fence between them. So what we see here is a number of memory references occurring before the fence and a number of memory references occurring after the fence. The ones that occur before the fence have to wait. In other words, the fence has to wait until all of these memory operations are, shall I say, completely completed. And what I mean by that is regardless of what processor we're looking at these operations from, they are seen to complete before we go ahead and do the fence operation. So in terms of the architecture, a new instruction needs to wait until all older writes have been posted on the bus, if we have a bus-based system, or received an acknowledgement of invalidation otherwise. So in other words, the activity that's recurring because of the write has to complete wherever it is seen in the system. And not only that, but all older reads need to complete. In other words, all reads that have been started in the past need to complete. That means they need to return their value. And then the pipeline needs to be flushed so that other memory operations can't be issued before the fence instruction executes. And so that's what a fence instruction does. It basically says everything before this has to be finished, and then the fence instruction needs to execute, and only then can we start anything that's supposed to happen after the fence instruction. If we insert fence instructions wherever we need for some memory operations to finish before other memory operations start, then we can get by without sequential consistency. But programmers need to insert these fences, and if they forget to do it, what happens? Well, correct execution might not take place. You might have results that are impossible to get in sequential consistency. We've already seen sequential consistency, and we're going to be talking about a number of other consistency models. So it's important to have a way of diagramming these models so we can see how they differ. Suppose that the value of a particular memory word in processor 2's local memory is 0. So we have a situation like this. Processor 2 has a value in its local memory of 0. Then processor 1 writes 1 to that memory location. And then later on, processor 2 reads the word. But being local, the read occurs quickly and the value 0 is returned. What's wrong with that? Well, depending upon the consistency model, nothing might be wrong with it. But if we expect memory operations to be seen as soon as they're executed, in that case, P2 has retrieved an out-of-date value. Now, regardless of whether the program can tolerate a situation like this, reading an old value from in P2, the programmer needs to understand what can happen when memory is accessed this way. And this kind of situation occurs often in a distributed shared memory system. So if we're talking about a large system where all the memory isn't on a shared bus, then we have what's called a distributed memory system. And situations like this can come up when the results of a memory operation are seen in some places in the system before they're seen in others. And if you access them from one of the places where they're not seen, things can appear to happen out of order.